Good evening, all of you. I hope all of you are there. As usual, we encourage people to show their video unless you have a problem with bandwidth, because it's good to have, a visual interaction as well. And it's also nice to see these squares filled with faces than, just names, because that's very interesting for participating, and it will be very inspiring. So I request, if you have no other problems in showing the video, please show your video so that the speaker can speak. And it's not very often that we get speakers like today's speaker. So I request all of you, if you have no problem with the video, please show your videos so that speaker can see you, and you can of course see the speaker even otherwise. So good evening, all of you. My name is Sangeeta Menon, and I first welcome all of you audience along with my team, Niharika Sharma, Meera Menon, and others. And it's a great honor for me to say a line of welcome to my friend, Dr. P.G Madhavan, whom I have known for many years and whom I have admired for his scholarship and his brilliance. And I have not met many people with whom I can discuss consciousness in the context of artificial intelligence and all the latest theories. And he keeps abreast of the latest literature, and definitely you have a brilliant mind here today. And please remember that this is 2:30 a.m. for him in Seattle. And so it's a very big thank you to Dr. P.G. Madhavan for braving this sleep and all the difficulties to be speaking at this time and to be with us at the National Institute of Advanced Studies. So warm welcome to you, Dr. Madhavan, once again. And Niharika, now maybe you should proceed to the next step.
Thank you so much, ma'am. I'll request Meera Kumar Menon to give a brief bio. I think we have a huge bio that we can say good words about P.G. Madhavan, sir, but I'll request Meera to say something. And also today's session will be chaired by Dr. Nitin Ragraj, a faculty with our team. So welcome to you also, sir. Meera, please, over to you.
Thank you, Niharika, and a very warm welcome to you, sir, on behalf of Team CSP. We are very glad to have you here today. Dr. P.G. Madhavan is the CXO of Phase Open Inc., an AI and robotics company. He's a technology and business native, grown up within multiple careers as startup founder, corporate officer, technology leader, and university professor. After acquiring his PhD in electrical and computer engineering from McMaster University, Canada, his academic career at University of Michigan at Ann Arbor, Indiana University, and Waterloo University focused on original research in computational neuroscience, random field theory, and applied systems theory. Rest of his career has been in industry spanning major corporations, Microsoft, Lucent Bell Labs, GE Aviation, Rockwell Automation, and NEC, and 4 startups, 2 of which he founded and led as CEO. Currently, his activities are in the areas of data science and machine learning in the Internet of Things. He is a champion of casual digital twins. So we are very, very honored to have you, sir, and we look forward to hearing you speak on digital twins, the present and future.
Thank you, Meera. Shall I start then?
Yes, sir, you can start now.
Okay. Irrespective of what Sangeeta said, I'm delighted to be here, even though I say it's a punishing hour, 2:30 a.m. in Seattle. But when my dear friend Sangeeta invites me, there is no hesitation. I have to accept. So a big thank you to my dear friend and head of your consciousness studies program, Professor Sangeeta Menon. Also, thank you to Chairperson Dr. Nagaraj. Now, Meera and Niharika has been very helpful in helping me set up and organize this talk. So I really appreciate your help. And more than anything, thank you for the audience. I see a large number of folks. Some of them I recognize, but this may not be the right time to thank each one of them individually, but collectively, thank you for the audience. I really appreciate it. So when Sangeeta mentioned this talk, I thought, what has consciousness got to do with digital twin? So am I supposed to talk about digital twin and its physical twin? And do they share a consciousness? That's above my pay grade to discuss. I'm not qualified to do that. So then the next thing that turned out in my mind is causality. So cause effect, this has been a preoccupation of human beings from a long time ago. So it's a big deal for NIAS and this particular group. So I think it's very relevant. However, I do not plan to get into the middle of Hume and Kant and all the debates that they've had about causality. This would be a much more, mild form of causality discussions. So that, I guess, is the tenuous link between my talk and your professional work of most of the people in this group. So just to spend a little bit of time just clarifying the causality issue, this is one of my favorite cartoons that distinguishes, in statistics, we always say correlation is not causation. This picture makes it amply clear. But another way to think about it is, let's say we have two things, say blue and green, A and B. So if those two are correlated, the relationship between them are not directional. They are correlated. It's not one correlated with the other, that directionality does not exist. But if you look at the second case here, so let me get a pen or a laser point. So if you look at the second case here, so let's say this is dog, this is man. This is dog bites man bites dog, man does not bite dog. All three are very informative. Sorry to overlay an old joke on causality, but the idea is there are multiple relationships, and here there is only one relationship. So correlation is the basis of all the big machine learning advances that you hear today, like deep learning, all the remarkable breakthroughs that are happening. It is all based on correlation, because causation, finding the directionality of what affects what, is hellishly difficult. Fortunately, there has been some progress, but let us tread softly. And I'll introduce the subject by relating a story from my childhood. So when I was a wee lad in Kerala back in the 70s, my father had this, ratty old car, and it is more often in the shop than on the road. So we would take it to our neighborhood auto mechanic, right? His name is Kannu. Kannu is like a huge figure in the life of people who grew up with me. He's this huge guy. So the story is that if he wants to inspect the underside of the car, he would just hold one side of the car, lift it, and look under it was that big, right? And he's a master mechanic. So we take our car in, engine is not running very smooth. Of course, that my car's engine didn't look anything. My dad's cars didn't anything like this. It was old jalopy. But so the apprentices would run around, poke things, and listen and so on. And then Kanu will make his appearance. So Kanu will come, look at a few things. Then he will take his trusted stethoscope. Actually, I've seen this with my own eyes. He lifting a car, that is probably apocryphal. I don't know. I have not seen it myself. So he would listen to the engine through the stethoscope. He's listening for, he's a master mechanic. The tappets making little noise, the bearings on the crankshaft making noise. So in his mind, he forms a whole model of what's going on, and a causal model. What is causing what? So based on all that relationship, he would say, well, go and increase the few clicks on the timing belt. All of a sudden, the engine would purr like a cat, runs beautifully. So let me map that into today's terminology that I want to use in this talk. So that stethoscope and listening device, that sensor, That is what you would have heard. There is a lot of conversation about something called IoT, Internet of Things. You connect sensors on all kinds of devices, then bring all the data back into the cloud and analyze it and so on. So that is like the IoT, the stethoscope. Then he forms a mental twin, as we talked, his acoustic and institutional knowledge that he has developed. He has ability to know what would be causing what. So he forms a mental twin. I'm kind of trying to get to digital twin here. And then using that information, he does say, go do this. He prescribes an action. That's called prescriptive analytics. So there are two, three terms that comes together all the time: AI, machine learning, IoT, analytics, and now we'll talk about digital twins. So they all have different applications and sense. But thinking about digital twin, AI to me is a marketing term. What's really underlying artificial intelligence of today is machine learning. This is the real mathematical part, algorithmic part of AI. So when I say AI, just think of machine learning applications that you hear about in the press and in your academic journals and so on. So a little our participant count is increasing. Okay. Uh, so just to level set very quickly, physical twin, we all know, be it a motor. I have taken industrial plant floor things or a CNC machine, or the last one there is called flexible manufacturing system. But this could actually have been, the lungs of a COVID patient. That's a physical object, and it can have a digital twin. So the simplest form of digital twin, which again you may have heard, is we call it a dashboard. So all that information that was collected by IoT, like the stethoscope in Kanu's case, but with temperature, pressure sensors, various other devices, all that data in an IoT system, we bring it onto the server, then bring it onto a client's screen in the form of heat maps and bar charts and so on. So by one glance, and visual system is very powerful in detecting anomalies and changes, you can see the condition of whatever the dashboard is reflecting, that motor or that CNC lathe or what have you. Now, there are complex digital twins. When I was at GE Aviation, we had a complete digital twin of a jet engine. This is just a caricature of that. So all the fluid dynamics within the hot path of a jet engine is modeled by Navier-Stokes equation and other fluid mechanics, fluid dynamics, theory, and you can actually uh, reproduce. So it is like a proxy of the real jet engine that's flying, and we get continuous data from the jet engine, and we have this computational model, and we can compare what's going on. In fact, I have used it for detecting some very complicated and hard to figure out faults within the jet engine during my work there. The other one you would have heard about, a big thing in India, especially, I think, is so-called smart cities. So the same concept, IoT, you put sensors all over the place, buildings, street lights, traffic signals, water supply, all of that. And all that data is coming into this city headquarters. So think of it like the old NASA Space Center pictures. You remember, a lot of screens and all the activities there. That's a digital twin, even though we didn't call it that. So in this very fuzzy definition of what a digital twin is, my opinion and the way I think about it is that is the appropriate home for things like visualization, machine learning, analytics, all the things that we do to the physical twin. As I said, I simply showed some mechanical stuff. This could be very much an application in a medical field. It could be like I said, a lung, and the digital twin is its effects of COVID, perhaps, and so on. So you get the idea of this comparison. Now, I had a small problem in the sense that I don't know the level. We have probably a mixed audience. So some of them may be a little too basic. And later on, some of them may be a little too advanced. So I'll try to go through it and try to make as much sense as possible. In the end, of course, we can come back and talk more about it. So, like 20 years ago, way back when, I used to work for Rockwell Automation. That's a preeminent company in, industrial plant for maintenance, measurement, all of that stuff. And we developed an IoT. There was no IoT then. There was no digital twin then. So we developed this software. So what you're seeing is actually one of our, case studies. One of our customers, Georgia Pacific, a large paper plant. So we go and take a digital picture of their plant, and then the foreman who's sitting, I don't know, many miles away, on his computer screen, there will be the plant digital picture. And the points that we are monitoring, it'll be color coded. If it is green, everything there is going on. So at these points, we have embedded sensors, and that data is coming through a network onto those days there was no cloud, but to our server farm. And then we are looking at these things. So for example, if something is red, the foreman can click on it and can see historical tables of what happened. In fact, we had the coolest thing where you could double click on it and actually see real-time data, vibration, temperature, all those things. So we had actually managed to do this with a plant in China sitting here in the United States. And this is 20 years ago, very exciting. So this is how it is used in typical industrial situations. Now, if you're a novice, you may not have these name confusions, but if you have read about it, heard about it, there's a bunch of confusion. So let me clear that up first. In general, we talk about assets and systems, right? Assets are single things. So like I said, could be a motor. System could be a flexible manufacturing system. Asset could be a lung. System could be the patient who is in ICU, and so on and so forth, limited only by your imagination. So digital twin is used primarily for two things. One, production of the asset. That is actually designing, building, how thick should the metal parts be, where should the electric supply go, all of that. So it's a production of the asset. The other one is using this motor. You're going to use it for something, right? That's the production using asset. This motor may run, say, a lathe. And on a lathe, let's say you are, smoothing out a metal rod. So it is really used for the production of the metal rod. And the asset component that leads to the production. So most of my work is in the latter category, in B. So it's using production of the asset. Now this part of late in the last 5 years that is using digital twins to design equipment assets have really blossomed. I mean, there is a company called ANSYS, you may have heard. I mean, they model all the thermal distribution, stress distribution, the strength, this, that, and you can completely design. 10, 20 years ago, this was done by what is called CAD-CAM. There is no more CAD-CAM anymore. It is using these digital twins that all the designs are being done. Not all, majority, and everything is moving industry in that area, very advanced. There's other using production using the asset is still in its infancy and it is coming, but you can tell it is super important because how many metal rods can you process? If a small company, workshop in your neighborhood, if they have this IoT and this analysis, they could probably increase the number of rods they produce or improve the finish of the rods so they can sell at a higher value and price and so on. So it's very important for the coming automation of industrial operations. Now, confusion in twins also. There are so many names floating around. So about a few years ago, I put this out as a way to kind of get everyone's hands around it. Let's agree to some terminology. There are three things that you hear usually. Display digital twin. Display digital twin is nothing other than that dashboard that we saw. So there is a physical twin there. It's whatever activity you're sensing, you have it displayed on a screen. That's your display digital twin. So think of it as a proxy at some level. A more improved proxy is this forward digital twin. I'll talk about why it's called forward, but it's basically simulation based. This is like that jet engine simulation I talked about. That is a forward digital twin. The new thing, and the thing that I'm working on, is called the inverse digital twin or causal digital twin. It's a big deal to me, and I believe it is going to be a big deal for the industry. Causal, back to that causality, we talked about it's not correlation. What is causing what? And I'll describe why it is hellishly difficult to do. But if you're able to do it, and I believe we are, the payoff is great. At a very high level, display digital twin helps you assess machine status, the high level. Is it working? It's not, you cannot do too much digging. Using forward digital twin, you can go a little bit more and find machine faults to some extent. But it is with the inverse digital twin that you can do kind of what if analysis. And that is crucial when you have an agricultural field and its digital twin. You can do that. And we've done that. Or you have a jet engine. So you can say, if I change this, what would have happened? Based on that, you can go and say, Kanu will say, go and do, change your timing belt. So it is that kind of prescription that is the real payoff in this digital twin. Others are definitely helpful, and they're not independent. Each one is built on the previous one. So it forms a kind of a spectrum of value add as we go through it. So yeah, what is this difference between these two? The best way to explain that is with a neuroscience example. As Mira had mentioned, I have a neuroscience background also. So let's say you have a headache or something, you go to a neurologist. She may say, oh, go and get your EEG. I don't know how many of you or your friends or children have had this thing, but I hope not. But they will go and take the EEG. EEG are these squiggles, they put electrodes on the scalp and you can see all the, squiggles. It tells the neurologist something. But what the neurologists really want to know is what's going on inside the brain. And for a normal working human being, you cannot go stick stuff in people's brains, right? So for example, if the neurologist suspects the child has epilepsy, what she wants to know is where are the foci, the epileptic focuses, because that is where they may want to go and do stimulation or do surgery and so on and so forth. So the inverse problem is see what's on the surface. So that is like getting IoT sensor data and figure out what's going on inside the brain or inside the machine. As you can imagine, if you cannot cut open the brain, that's very hard. You cannot cut open the brain. You cannot cut open a motor that's running. Very hard. The forward model is the other one. That is, if somebody was able to tell you these are the foci and loci, locuses within the brain, and they are coupled in this fashion, and the coupling changes based on disease conditions, then you can actually almost generate the EEG that will see on the surface. Conceptually, that should make sense. So the forward model, where you predict the effects on the surface, knowing the deep causes, is a simpler problem than the inverse model. That is, you know the effects and you got to figure out what caused it. So the brain is an example. The other one is classic one is in seismic studies, an earthquake. So same things like the brain, right? People put those phones, they sense vibration and then listen to the various earthquake activity. Based on that, their interest is not just the surface vibrations. They want to know where is the plate tectonics, where is the plate slipping, where is whatever else is going on inside the earth. There's no way to go and actually look at that. So that's a hard problem. Just want to spend a time to really understand why it is a hard problem. In mathematics and engineering and science, we call it an ill-posed problem, which is a hard problem. So here is a simple cartoon example. So let us say, we have a meter that measures that sound I talked about, like in the earthquake case, right? So all it can measure is one point, at one point, the sound that comes. But really underneath, so this one is, you cannot look below this brown, you know, plane, right? It is blocked. There could be big sources, small sources. They could be coupled. We don't know the number of sources. We don't know the coupling strength, but all of them is happening. And whatever it is, all those sounds impinge here, and you get a reading. So all you have is the reading. So the ill-posed inverse problem is, from that reading, go figure out, to begin with, how many sources are there. Is it 3? Is it 2? Is it 50? Don't know, because we cannot probe into the brain or into the crust of the earth. How are they coupled? That is a big dynamics issue. So these things are not sitting there. They are, in the case of brain, there is connectivity that, some pathways, if they are more excitatory and they are made more, what shall I say, conducive to transmission, they would have a huge impact. And that could change because of medication, disease conditions, and so on. So coming from the surface to the inside is a hellishly difficult problem. In fact, you could have infinite number of combinations here that will all give the same reading there. That's why it is called an ill-posed problem in mathematics. But there are some solutions. There is a mathematical approach called regularization. I won't spend time. People who are from the math department would know something called Tikhonov's regularization. Basically, it is some, a minimum norm solution. But the point is that it's mathematically satisfying, but it may have no bearing on reality. In this case, it may actually say there are only 2 sources and they are coupled extra strong or something, because additively it gives you the same reading here. So it may have no bearing on reality. So, and there is no real way to test it. Now, the approach we take is what we call a systems-based or model-based approach. So we go and talk to a canoe and in conversation find out what is the causative, cause and effect chain of events that you as a domain expert know, right? And draw it up as what we call a graph causal model. So we have constrained the solution to some extent. The moment solution can be constrained, and constrained in meaningful way, this ill-posedness will reduce. We can reduce the complexity of solving. Going from here to here can be improved. That is ultimately what our approach and methodology does. Now, in this area, there is this work of Friston. Friston is a neuroscientist in London. He has done tremendous work in this area for brain. So, and he has created this infrastructure called dynamic causal model. In his case, it's again EEG measurements, but his forward model, like our graph causal model, is the hemodynamics of the brain, which are pretty well developed. That's the blood supply and the blood flow in this. Then he correlates that information with fMRI. fMRI by itself is not enough because its resolution is really poor. Temporal, it's a resolution of like minutes. What we need is milliseconds probably, at least hundreds of milliseconds. That's how fast things happen in the brain. The resolution probably is inches. What we not need is millimeters or even less in the brain. So just fMRI isn't enough. So he brings in the hemodynamics for the forward model to constrain the measurement from the scalp to figure out what's going on in the brain. So over the 20 years, he has produced this really great body of work under the title of Dynamic Causal Model. Either he's a great mathematician or he has a team of great mathematicians. So it's just an amazing kind of work if anyone wants to follow that. My work does not follow his exactly, it's much simplified. We are working with motors and stuff, not human brains. So we can be a little simpler. So, and in my work, we focus on what's called the dynamics of the situation. So if you're focusing on the statics, that is a structural thing, like you talked about how thick should be the metal on the motor and how big should the bearings be, all those decisions. That is the static modeling, structural modeling, which is used for designing and building motors. My interest is when that motor is operating, that is the kinematics and kinetics. That is when things are rotating, things are doing things, there is load on it. what are the things that happen, what are the things go a lot with coupling. The coupling changes is indicative of what's going to happen in the future. It is that, again, connotes causal relationship between various things within the motor, which is going to be a key part in predicting, prescribing how to use that motor in the long-term future. So these are the key pieces: graph models, causality, couplings, and interactions that we focus on. So in putting this to use, it's nothing like an example. I don't know how much of you are mechanically oriented, but this is the area I come from, so we'll talk about that. It should make sense. I'll try to make sense of it. This is a cutaway view of the motor. You know, there are bearings and there is a shaft and there is the housing and all that good stuff. But what we do typically to monitor, like in that Rockwell automation case, we'll stick something called an accelerometer. I mean, this is not to scale. We'll connect it to the body of the motor. So what we get is this measurement, this vibration. It's like that EEG you get from the scalp, right? So you have just the surface information. What we want to figure out is the key components in a motor are the shaft and the two bearings. These are the things that can go bad. For example, if the shaft is not perfectly aligned, if slightly bent, it'll affect one bearing more than the other. Then the coupling will drive this into unstable situation, and the whole thing will fall apart and the motor can burst. Or, we want to know much earlier so that we can go and align the shaft, and then things would be okay. So from this surface measurements, we want to know what these couplings are. They are sometimes called virtual sensors because there is no actual sensor there. It is just this vibration, but we are abstracting this information. So to do that, we create this what is called the Graph Causal Model. So we know the shaft will affect the two bearings, the bearings will affect each other. So K1, K2, K3, these are the various couplings. So from this squiggle, our case is to figure out what these virtual sensors are telling us. Because in this case, with consultation with domain experts, we know those are key parameters that will explain how this machine is working and how we can prescribe action based on it. So to do that, there is a big infrastructure that I bring into it. This has things called Kalman Filter, a neural network. You may see some familiar things. Now, I would have spent more time on it if we had people from Indian Institute of Science, School of Automation. This is the kind of things they know. I don't know whether School of Automation still exists, right? They changed? Sangeeta, do you know? This is a famous school in IISc. I think they have changed it.
I think Nitin might be able to say that. Nitin?
Yeah, CSA is still there, sir. Computer Science and Automation. I think it still exists. Yeah.
Yeah, in olden days, it was called School of Automation. And I remember this from my childhood days. There was this towering figure, both figuratively and in reality, Professor Krishnan, I believe. He was a master, he was a guru of systems theory and one of our, people we we pray to, kind of thing. It was a fantastic department. So this is kind of thing that I would talk about at length with those folks who would appreciate it. Know that I will point to information if there are technically oriented folks where we can dig further. But given the time, Niharika, what is a quick time check? I have how many more minutes?
So 5 to 7 minutes.
Okay. So why are we doing all these things? What is the purpose of this? So now I'm going to take a completely different application. Agri-tech or ag tech is actually becoming a big deal. In fact, I worked on this when I was at NEC in Tokyo. So, we used to monitor these huge cornfields or tomato growing in California and Portugal and Australia. So the field is completely instrumented. There are things that measure moisture. There are things that measure NO3, nitrogen. That's NO3 is the key in growth, and weather. We have satellite information. And we can create a model, a digital twin of that, a simulation digital twin. It's called DISAT. DISAT is a well-developed, multi-decade developed software that will, allow you to run the simulation forward and kind of see what's going on. So my approach from the graph causal model would be, so this is based on the genetic potential of the seeds and so on. We created a simple graph causal model. So the reason why we do this is there is no other method that will allow you to answer these questions, such as, you know, what is really driving the yield? Now, if I decrease irrigation or increase fertilizer, what exactly would happen to the yield? Because these are correlations won't cut it, because it may be correlated with rain, this, that, other, and correlation doesn't tell you which direction. Remember, is it dog bit man, or did the man bite the dog? You don't know, right? So that is critical in being able to answer these things, because based on that, there could be a business objective. This big industry who runs this ag fields may say, oh, we have to cut 10% of expense. So the question is, can we reduce irrigation and fertilizer by what amount so that the yield reduces only, say, by 10%? So we are still okay, but we want to really reduce the other. If we don't know and we're doing it like open loop and trial and error, reduce it too much, yield goes to 50%, and they are in big trouble, right? So we can do much finer things. That is the power of prescriptive analytics and causal digital twin that will lead to those kind of answers. So at a bigger level, at an industry and as an ecosystem level, what is the real concern? I'm personally very concerned. That's the first part of this IoT, display digital twin, predictive analytics. It has really grown very rapidly. In fact, in the United States, many of the large corporations have all of them already installed. They are working. They are not probably getting the full value out of it, because at this point, the customer CEO would come and look, okay, great picture, dashboard. I see all these heat maps. So what? What do I do with the business? What should the next thing that I should do? I think the fault lies in this. We have not accounted for causality. We have not crossed this chasm. And it is when we do that we get to prescriptive analytics, and we will be able to say, if you do this, you'll waste less. If you do this, your product quality will increase, so you can charge more. Then your gross margins, gross profit will increase. That's when the customers say, IoT, digital twin, all these things are really useful for my business, and I'll spend the billions of dollars required for this to go forward. We are not there yet. And if we don't get there, my worry is that this is the famous market research Gartner hype curve. We don't know where we are at this point, but if we don't solve this causality kink, I'm afraid we will go into this what's called the trough of disillusionment. Then the industries usually take decades to get out of it. So I'm trying to see whether, working on this causality thing, we can kind of minimize or eliminate this trough of disillusionment. So at this point, my main topic of conversation is over, but I've heard that, and I know that India has become a country of entrepreneurs. So I want to take 2 minutes to talk about, I don't know whether there are any budding entrepreneurs in this audience, but want to give you some idea about how to do startups based on what I just talked about. So, and I'm willing to give free advice and some sort of mentorship to folks who want to contact me to produce new and killer startups that'll make a real difference in life of Indians and all over the world. So the first is digital twin. You know about it. What I call a digital twin exchange, or digital twin, a DTX. It's what's called a two-sided marketplace. Two-sided marketplace. Venture capitalists, VCs salivate when they hear two-sided marketplace. Why is that? Because this is the model of, let's say, Amazon. There are sellers, there are buyers. Amazon brings them together. See how wonderful they're doing in business. Or Uber, there are drivers, there are riders. They brought the people together in the middle. That middle, DTX, is where they interact, and every business model that is the two-sided marketplace has uh, taken off like crazy. So digital twin exchange could be such a marketplace for people who make all these motors, this, that, the Bosch and Siemens and other big companies. And there are so many mom and pop and big, Tata factory operators. They probably are already doing it, but smaller companies, and they don't have the access. So they can go to this middle where they can do that exchange, and the business can be set up to do it. And I have some more ideas about how to do that business, which somehow, oops, this is what I call business stack. I won't go into the detail. How do you make money? Who does what? OEMs and startups, what role do they play? All of that stuff. I'll be happy to talk about to a few select, very dynamic and interested entrepreneurs. Now, everything I talked about here has very strong intellectual antecedents. The main name is Judea Pearl. We have thought about cause and effect for time immemorial. The Stone Age man also would have wondered about it, but nobody had put that on a framework until in 2000. Judea Pearl took on that task, and he was called a crackpot, and nobody believed it, and all of that stuff. But then in 2014 or 2016, he won the Turing Award, which is the award for the Nobel Prize in computer science. So now everybody is causal. So much so, you may have heard I call them the three amigos of artificial intelligence, AI, Bengio, LeCun, and Hinton. They're all now talking about, oh, AI needs causality, because now, because it's only correlation. We had to bring in causality. How do we do this? Bengio especially leading that kind of activity. So at NEC, I had a fantastic researcher, Dr. Chun Chen. Chun Chen is a master in this. She's young, young and upcoming, but abstracted the work of causal. So some of the underlying mathematical apparatus has been developed by Chun Chen. And I talked about Friston. So I skipped all the hardcore info in my solution. You saw the Kalman filter and all of that. You can go to this article to get the real hardcore info. So with that, I would like to thank all of you for patient attention. I'm not sure how much I was able to make that appealing and interesting to you, but just know, if you take away a few things, something you know very well, correlation is not causation, but then the question is, how do we bring causation or causality into the various things in AI and machine learning that we do? Because from this talk, know that you get a step increase in value if we are able to do that. So with that, thank you once again. Appreciate your attention.
Thank you so much, Dr. P.G. Madhavan, for this very, very, what should I say? I mean, I'm not at all expert in this area, but I can see how deep your knowledge is. There are three people, I'm sure, who can talk to you in this audience. Of course, one is my colleague, Professor Nitin Nagaraj. The other is his own student, still not doctor, Anand Ganesh, who is a doctoral scholar with Nitin, who has worked with Facebook, and he's an engineer as well. And then Dr. J. Krishnan Divakaran, who is also an entrepreneur and from Kerala, also working with schools. And I'm sure there must be a lot for you guys, you folks, to say. So Niharika, maybe in that order, perhaps first Professor Nitin, since he's also chair, and then Anand, and then J. Krishna.
Yeah, thank you, Dr. Madhavan. I mean, very insightful and lucid presentation. I mean, in such a short time, you covered such a complex topic. I think that itself is a great skill, and thank you for this presentation. We have some interest in causality, and we have looked at DCM and other model-free methods as well, but in the context of neuroscience and econometrics and other time series. So one question that I had was, when you talk about all these industrial systems on which you want to do this causal based analysis, right? One of the objectives would be some kind of anomaly detection, right? Anomaly or say fault detection, or so there you might need a lot of data, right? I mean, how how good your models are in terms of how much of data do they need? Do they need lot of data to build this causal model, to estimate those coupling coefficients, or how data hungry is it? That's the kind of question I'm sort of interested in knowing.
Very good question. And the quick answer is needs lots of data. Anything in machine learning needs a lot of data. Now, one thing I would add or differ a little bit is the use of these techniques for anomaly detection, to me, is the minimum, floor. That's, I have this personal thing that, okay, people have solved it, we can solve it, but what I'm looking for is performance, not just fault detection. Is it dying or is it, no, if it is a patient, how can I make them healthy? So it is performance that I'm focused on. That is when the value of all this extra work, data that you have to collect to do causality really pays off. Anomaly detection, we can almost do it, like that jet engine, very complex issue, but we have an existing simulation software called NPSS, which NASA and others and GE, we all developed it. And it's very powerful and very complex, nearly impossible detection as the jet is flying, we were able to do. So fault detection, essential, absolutely must be done, but that is the first layer. So if you're going to spend all the time and money and effort to do causality, let's shoot for something bigger in improving performance, in improving lives and things like that. That would be my quick answer to it.
Thank you. Very, yeah. We're open to other questions, right? Yeah.
Yeah, I'll request Anand Ganesh to please proceed with his question or questions.
Hello, Dr. Madhavan. That was a very interesting presentation. I had sort of two questions. I'll tell you the second first, and you can go later. You mentioned this Kalman filter and so forth. I personally am very interested to know a little bit more about what you had intended to say there. Sort of, I'm an engineer myself, and I'm very interested in that. But let me get to question one, which I think may be a shorter answer. So when you do this causal modeling, I assume the sorts of things you do are use the junction tree algorithm and like how do you sort of predict what if scenarios, right? I guess that's the sort of thrust of graphical modeling.
Yeah, very good question. So in causality, so Judea Pearl started this, and there has been branches even before he did his work, or maybe there's something called structural equation model, SEM. That is a big tool set to address causality problems. Judea Pearls is that do calculus, a mathematical formulation. So there is a third branch, and that was the third reference that I've given. I forget the Japanese guy's name, Shimoni or somebody. So he had a third branch of tool sets. So Chin, my researcher who worked with me at NEC, she follows that school. So in other words, causality, there are multiple schools, right? So there is one school where the methodology we use, we find that is much less assumption based. So it is actually, we extract the graph models from it, but it is assumption free. In structural equation modeling, you had to put in all your biases and assumption first in forms of equation, then you go and find it, which in some cases is okay. But in most cases, if you go and put your bias into the data will tell you crazy things. In our case, it's derived from the data. The data generates the graph causal model. Then in that graph causal model, we can turn this knob and see how much the output parameter varies, the yield, for example. So it's a quantitative methodology which is new. So in this context, I would say if you look at Chinchin's paper that I had referred, and because it's a LinkedIn article, it is not that heavy, but all the details of the Kalman filter and even the algorithm may be provided there. There may be a situation where I can give you the software. I have it, so you can go and work with it if you like.
No, very interesting. Maybe I'll let the next questioner ask his question, and then I'll come back if there's more time. Yeah, very, very
And the
interesting.
last, thank you, Anand. The last slide that is up has my email address. So any of you, either on the technical side or the entrepreneurial side, please feel free to send me questions, comments, whatever you like.
Actually, one more qualitative thing. You sort of alluded to Friston's work in passing. And I briefly looked at his papers and they seemed very theoretical. So it's actually interesting that you're able to, it's much more dynamics based rather than probabilistic, if I understood that correctly.
In fact, that is my affinity. So he's a state space based model, system theoretic approach. Mine is a system theoretic approach. So I use all of that. That's why Kalman filter comes in naturally because of the state-based approach. I've been impressed with Friston. He must have a tremendous team with him. And over the last 2 decades, they have really developed it quite a bit. Good to follow Friston.
Yeah.
Thank you so much, Anand. Thank you, sir. Meera, I'll just for everyone's notice, Meera will be opening up the WhatsApp group and will be sharing Madhavan sir's details. So anyone who wants to get in touch with Madhavan sir and couldn't get his email ID, Meera would be there providing you with the details. Now I'll request Jay Krishnan sir to please proceed with his comments and questions.
Yeah, thank you, Madhavan. It was a very insightful, talk. In fact, for the last 1 year, I had been following this area very closely. I'm a social entrepreneur and a system engineer. So I am trying to use this, for some of the environmental engineering, areas, because there are a lot of areas like solid waste management, then, sewage treatment plants. So these plants, my idea is basically to model as, digital twins, and then try to, fine tune, their optimize their operations. So I'm just a novice in this area. Maybe, you will be a mentor for me now based on whatever I hear from you. So my question is, you mentioned about a platform called ANSYS. I also try to understand their twin builder platform, which is pretty expensive. Do you see any other open source platforms or any competitive platforms which are affordable for social entrepreneurs like me?
Simulation platforms like ANSYS are super expensive. Mentor Graphics have a similar one. The reason is that they do finite element analysis. These are heavily fluid dynamics, heavily computational. They probably need supercomputers to do it at the back end. So, and they have some reduced model order approaches to it so that it doesn't get out of hand. But generally, they cater to major corporations. So if Siemens is designing a new transformer, they would probably use ANSYS to do thermal and electromagnetic and all of those analysis during the build process. Now, Preet Banerjee is the CTO, is a friend of mine of ANSYS. I would have imagined that these days everybody has a corporate social responsibility and they want to encourage entrepreneurs and social, especially with social costs. So it may be worthwhile just, sending an email to Preet and asking him, saying, do you have a scale down or some version that social entrepreneurs can use? But Jay Krishna, I would say, the causal digital twin is even better. So we can talk about it.
Yeah.
I'm an evangelist for causal digital twin. So, I can talk to you about that at a later time.
Yeah, thanks. And one more question on the process. So what I understand is there is a physical system. So we start with a model. Model belongs to the scientist category because they have to write equations, mathematical modeling, and then you are going to connect with IoT sensors from the physical world. And then what I understood is this model is going to evolve over a period of time. Based on the data, which is coming, from the real world using machine learning and things like that. So my understanding, is it correct? Because I never played with a tool. Though I have ideas in my head, I want a tool like ANSYS, to play with, to realize a small system and see, how this continuous loop, and learning, happens. So, yeah.
That actually you will find it very hard. So that's again the difference in the solution that I showed very briefly. It is a continuously learning system. Kalman Filter and associated technologies are, they're continuously learning. So as data comes, uh, if data changes, the parameters would change, the couplings would change. And that is the reason why my solution focuses more on the dynamics, the, as I said, in your case, the dynamics of it, or in some mechanical system, the kinematics and kinetics of that piece of equipment. The ANSYS type of solutions will not address that. They are more of, static, what is the stress distribution, and so on and so forth. And they're not continuously evolving. So it's a bit like supervised learning. You use all that data, you machine learn, then boom, you got a model. In general, it's not continuously learning. You could, of course, retrain it with new data, but I work on, and Anand may be familiar with this, adaptive systems. Kalman Filter is a quintessential adaptive solution. So it continuously adapts. Now, in some cases, you would say continuous adaptation is really not necessary. A motor, which lasts for 10 years, not changing from minute to minute, millisecond to millisecond. So you need to only monitor this once in a while. So there are some applications where you need to, maybe in the case of a patient, a condition is worsening and should be moved to the ICU. You do need this kind of continuous adaptive estimation of the various issues. So again, I think ANSYS may not get you what you want as at a high level thinking. So perhaps if you would like to get in touch, I can maybe dig into it some more.
Yeah, thank you so much.
My pleasure.
Your connection with you itself, will be a real eye opener for me. Thanks.
My pleasure. Thank you.
Thank you so much, sir. Yeah, I think as we're running a little short of time, we'll allow one more question. I'll request Mr. Aditya to please proceed with this question. Yes, sir. Please go on.
Thanks, Dr. Madhavan. Wonderful talk. I'm actually currently at the University of Sheffield. I was earlier in Tata Institute of Fundamental Research and in National Center for Biological Sciences in Bangalore. But these days I'm at the University of Sheffield as a lecturer, just an assistant professor. So I'm also on this, on the topic of, say, the intersection of machine learning and neuroscience, computational neuroscience and control theory. And I've been working a lot on model-based reinforcement learning, and lately planning to get into causal model-based reinforcement learning.
Yeah, good.
And I was really surprised to note how much even in industry, how much you have developed on causal model. Because even in academia with Judea Pearl's causal inference is not so far back, and it's still a much an active area of research. So very great to know this. I will certainly get in touch with you over email. So that's the general comment. Apart from that, I was keen to know whether you only, do you use a linear model or do you have non-linearity as well, or and how much does that affect?
Yeah, the methodology accounts for, so just looking at the high level, there is a Kalman filter piece and a neural network piece, right? So at a without getting deep in, you could immediately see the Kalman filter is a linear solution, right? It's not nonlinear solution. So it is used for initial part of it. Neural network, of course, is a nonlinear mapping solution. So it is a combination of both that my solution contains. Now, those are critical things, not only nonlinearity, non-Gaussianity is a big issue to, so the probability density function is not Gaussian, handling them becomes very difficult. Now, Chunchen's work has specifically addressed those kind of, either her or Shimoni, the previous guy, work has addressed non-Gaussian situations. So these are hard. And your first comment is very interesting. So do not get the impression that this is well accepted and people are using it. I'm at what I would call the bleeding edge, or maybe even beyond the bleeding edge, just edge. I'm not even bleeding. So I'm evangelizing and championing causal digital twin. And the reason why I believe in it so much is that at NEC, Chin Chin's research work, I took that and incubated and created a startup and then spun it out. So actually, I should have mentioned that. So that startup, it's my baby in some sense, but I'm not connected anymore. They have all this software. So Jackishnan, this company I'm going to mention, instead of ANSYS, you may be able to use their work directly. The name of that startup is Inguo, INGUO, Inguo.io, Inguo.io. So Inguo has codified and made it into a tool. It's an API call, and you can do, you give the data, you'll get back the graph causal model. Then you can do what if analysis. It's another API call. And I mean, they're in the business, they're a startup, right? So they may not give it to you free. So we'll have to work through those kind of details. But that is the reason why I picked up on it and started working on causal digital twins. So this is by no means common or or well accepted technology, but it is inevitable, in my opinion, to go beyond that chasm and really bring value to businesses that have spent billions of dollars in IoT.
Yeah, thank you. I'll
Thank
be
you
in
so
touch with you.
Thank you, sir. Yeah, I'll request if there are any other questions, please you can raise your hands or you can type it out in the chat box. Um, Nitin sir, do you have any other questions or?
No, nothing at this time. We'll be in touch with Dr. Madhavan. I think me and my student very interested to discuss more with him, but we'll do it over email and yeah. Thank you.
Yeah, thank you, sir.
And either Niharika or Mira, if you could type in that name of the company, inguo.io, so that it could be in that whatever information you're going to share with everybody. I would recommend anyone, and they have great tutorial on causality, how this is to be done, all of that stuff.
Okay. Oh, okay, sir. I think, so when Mira opens up the WhatsApp groups for discussion, she'll be putting up it on the groups for everyone to see and have all the details there.
Perfect. That'll be wonderful.
There are any other questions, please raise your hands or type it out on the chat box. So there are many compliments for your lecture and for your presentation by a number of people in the chat box.
I appreciate that.
If there are no questions, we would like to end today's session with a vote of thanks by Meera Kumar Menon. Meera, over to you.
Yeah. Thank you, Niharika. And
just wondering, before that, maybe as the chairperson, Dr. Nitin may like to say something more, or it's a technical topic particularly.
Right. Yeah, no, I think we would like to know more about the details of the work, and I thought I will get in touch with Dr. Madhavan because very fascinating, and we want to know because we have done some work where we have developed neural networks which use less data, so we might, I don't know whether that could be of use to your work as well. Brain-inspired machine learning. So I think I'll converse with him. But thank you very much, sir. I think you opened up a whole world for us. So really, thank you. Really appreciate that. Yeah.
Yeah, it's my pleasure. Again, remember, causality is super important.
True.
Meera, please.
Yeah. Okay, so on behalf of Team CSP, sir, we extend our gratitude and thanks to you for speaking to us. Even at this hour, you were awake and you made a very clear presentation for all of us. So thank you very much for that. And thank you, Sangeeta ma'am, for bringing such speakers to us. It is indeed a privilege to hear from people like you. And thank you, Dr. Nitin Nagaraj, sir, for chairing this session. And thank you, Niharika, Ashwini, and Abhishek for organizing this as well. Thank you everyone once again, and we will again see you next Friday with another interesting session. So thank you all.
I appreciate the opportunity. Thank you very much.
Thank you, sir. Thank you, ma'am.